Today, we want to talk about a gradient and directional derivative. Remember, the big idea is we have a function of two variables, and so we ended up with two derivatives, fx and fy. These tell us the rate of change of the function in the x direction and the y direction. But now that we have a whole plane of directions, we can't just get away with two derivatives. Back in single variable land, we just had the derivative, and it told us how the function was changing, and we didn't worry about direction because we only had one direction, the x direction. So now that we have two directions, we got to make sure that we can calculate how the function is changing in any direction. So we have 360 degrees worth of direction to check. To that end, we had to find a way to combine our two derivatives. And we built this vector called the gradient. So the gradient of a function is a vector where we have the x derivative times I plus the y derivative times j. The important things that we need to remember about the gradient is that the gradient will be perpendicular to the contour and will point in the direction of maximum increase. So if we have a contour of our surface and we draw a line tangent to the contour at a particular point, then the gradient will be perpendicular to that tangent. So that's what we mean when we say perpendicular to the contour. Also, it's going to be the direction of maximum increase. This makes sense since it's perpendicular to the tangent. The tangent indicates where things are not changing. If you follow the direction of the tangent, you'll be walking along the contour. If you go in the direction of the tangent, you're walking along the contour, and that's where the value of the function is constant. So if you walk perpendicular to that, we get the direction of maximum increase. If we multiply the gradient by -1, we'll have the direction of maximum decrease. So if one direction is the steepest ascent, then the opposite direction will be the steepest descent. So the gradient is a combination of vector. So the gradient is a vector where we combine the fx of xy and fy at xy. We can evaluate it at a point, and at that point, well, it'll be the direction of maximum increase, and it will be perpendicular to the contour. Those are the things that we want to remember about the gradient. So we have an example. So let's look at the function f at xy, which will be xy plus y to the third. Let's first find the gradient of this function, and then we'll do all this stuff over here, figure out what that means. Finding the gradient of the function is just finding the two partial derivatives of the function. So fx at xy, the derivative with respect to x. Now in this case, we're reading x as the variable and y is constant. In this first term, y is a constant factor, and so we're taking the derivative of x to the first power. The derivative of x to the first is 1x to the 0. So we just get the constant factor y. Y cubed is with respect to x is a constant term. So the derivative of y cubed is 0. Things change up a little bit when we find the derivative fy at xy. Now, x is constant and y is our variable. So in this first term, I have x times y, and x will represent a constant factor, and we're taking the derivative of y to the first power. The derivative of y to the first power is 1y to the 0 power, or just 1. So we're left with a constant factor, x. But in this term, or in this derivative, we want the derivative of y to the third, and since y is the variable, we get 3y squared. This is an old skill We learned this way back on 2 days ago. So we should be awesome at this. At least that's like how I think math students and math teachers think things work. Well, we covered it in class once and we did like 3 or 4 examples. They should be experts by now. What we want to do now is take the 2 partial derivatives and put them into the gradient. So the gradient is a vector. So the gradient of f at xy, at any point xy, will be fx times I, so y times I hat, plus fy times j hat. An important thing we need to do is make the distinction between the gradient being a vector and the 2 partial derivatives are scalar functions. I put in values x and y, and I come out with a scalar. So fx and fy are scalar functions. F is a scalar function. The gradient is a vector that we're building out of these scalar functions. So at any contour, if we pick a point on this surface, this gradient will be perpendicular to the contour, and it will indicate the direction of maximum increase. Now, let's look at the rest of what we have up here. So the rest of the problem, I asked you to find fu at 1, 2, if u is this unit vector. So when I put a subscript of x, take the derivative of f with respect to x, or the derivative of f in the direction of x. So when I write, this is an unfortunate choice with f and u, but oh well. When we have f sub u, where u is a vector, find the derivative of f in the direction of the unit vector u at the points 1, 2. So that's what this notation means. It's consistent with our derivative notation from before. So this f sub u of 1 at 1, 2 is the derivative of f in the direction of unit vector u. So here is the derivative of f and this is a directional derivative. It's the derivative of f in the direction of unit vector u. At the points 1, 2. So if I want to ask you for a directional derivative, I not only have to give you a point to plug in, I have to give you a direction to go. I need 2 things. Back in the halcyon days of single variable calculus, I just had to give you a point. I just had to say find f prime at 1, because there was only one direction. How does f change when x increases by 1? But now I have to say, here's a point, calculate the derivative, and here's a direction I want you to go. So this u, this is our unit vector. I forgot to label it as a vector. So this u is our unit vector. Remember that a unit vector means its length is 1. So I haven't told you how to calculate the directional derivative. It does have something to do with the gradient. So I have this gradient vector that we built, and I have this unit vector. So presumably the directional derivative is some combination of those two vectors. Also, the directional derivative should tell us something similar to what we had in the derivative. It should tell us how much f is changing. And f is a scalar function. So I got these two vectors, one telling what the direction of maximum increase, and some other vector u, which is just some direction in the plane. I've got to combine these two vectors to come up with a scalar that tells me how much the function is changing. So if we think about what we want, we can figure out how we're going to compute this. We want to combine two vectors and come up with a scalar, because the directional derivative should tell us how much the function changes, and the function is a scalar function. That's what the derivative was telling us way back in the day in Calc 1. It'll tell us how much the function increases when x increases by 1. We want this directional derivative to tell us the same thing. And we've got two vectors, and we want to combine them to come up with a scalar. And there's only one option. So the directional derivative will be the gradient dot the unit vector. We want to combine these two vectors into a scalar. The dot product is the one to use. Right now, you're just going to take my word for it. This is what you do. Take the gradient and the unit vector that you care about, find the dot product, and that's your directional derivative. This raises the question, why is it going to work like this? And my response right now is, right now, let's worry about making the calculation. Then we can check the calculation with our intuition and what we know about what the gradient is supposed to tell us. And then we'll start to see for ourselves why this makes so much sense. Beyond the pure mechanical aspect of I combine two vectors for a scalar, and the dot product is the only way we know to do that. All right. So let's make this calculation. I need the gradient of f at the point 1, 2. And I'll find the dot product of the gradient of f at 1, 2 and the unit vector. So the gradient of f at 1, 2 will be 2i plus 1 plus 3 times 2 squared times j. So 2i plus 13j. So at the point 1, 2, the direction of maximum increase is 2i plus 13j. So the directional derivative of f, the derivative of f in the direction of unit vector u at the point 1, 2 will be the gradient of f at the point 1, 2 dot the unit vector u, which is 3/5 I I could have just written u. Hold on. So my gradient vector is 2i plus 13j. And I find the dot product with 3/5 I minus 4/5 j. This is going to give us a scalar. So I'll end up with 6/5. Because I do 2 times 3/5, and then 13 times -4/5. So 13 times 4 is 26/52. And 6 minus 52 is -40 something, 46. What this means, if we're standing at the point 1, 2, and we move in the direction, and there's a certain value for the function. And if we move in the direction of 3/5 I minus 4/5 j, then we should expect the value of the function to decrease by 46/5. The same way that if we looked at the derivative of a function, a single variable, and the derivative is -2, if we increase x by 1, we should expect the function to decrease by 2, approximately. This is using a linear approximation. Some things to note. In the dot product, we have to make sure that we're using a unit vector. If I just ask you for a directional derivative, you don't have to be given a unit vector. But in the dot product calculation, you have to reduce your vector to just a direction. You have to reduce it down to a unit vector. So notice that what I mean is that if we said, for example, so note, U must be a unit vector. If you're not given a unit vector, you have to divide by the length to make it a unit vector. If your given vector is not a unit vector, then divide by its length. So that you can get a unit vector for your dot product calculation. So for example, if I said find, I didn't give myself enough space. So let's use the same function because I'm going to be lazy like that. Let's say I want to find f sub v at the point 1, 2, because I'm extra lazy like that, in the direction where v is 5i plus 12j. I want the derivative in this direction, 5i plus 12j. What we want to notice is that v is not a unit vector. So the magnitude of V is 13. Oops. The magnitude of V is 13. So a unit vector in the direction of V is 5/13 plus 12 I plus 12/13 J. So we want to use the unit vector just take V and divide it by its magnitude. The reason that we want to do this is that the dot product will carry as a factor the length of the vector. So if recall that the gradient of F at the point 1, 2 was 2I plus 13J. If I calculate the gradient of F at 1, 2 and take the dot product with the vector V, I'll have 2I plus 13J dot 5I plus 12J. So 2 times 5 is going to be 10, and 12 times 13 is 156. So we get 166. But here, V is not a unit vector. If I want the directional derivative, I'm going to take the gradient of F at 1, 2 and the dot product of a unit vector in the direction of V. So I have to divide by its length. So notice that in the calculation, I would just take 2 times 5/13 plus 13 times 12/13. I'm going to get the 166. It's just going to be divided by 13. So if you ever forget, you don't have to go back and redo the whole calculation. If Canvas is like, oh, that is incorrect, go back and check to see that the vector that you were given is a unit vector. If it's not a unit vector, just divide by the length of that vector. Any questions? All right, so how can we think about what's going on here? So we want to make sure that this still looks like we're using all the same words, derivative in a particular direction, that we used in Calc 1. We're using all those same words. And in math, words have to mean something. So we want to make sure that the way we describe things in single variable calculus translates to describing things in multivariable calculus. So let's recall what this looks like in single variable calculus. I'm going to pick an easy function because it's early. And I've had some coffee, but not all the coffee. So switching back to single variable calculus might not be very successful. Usually when I get stuck, I don't know if it's a more coffee problem or a less coffee problem, but I know what solution I always apply. So let's suppose that we're looking at the function f of x equals x squared at x equals 3. Oh, shoot. Let's suppose that f of x equals x squared. I want to find f prime of x at x equals 3. Notice I only have to give you the point. The 3 is like the point 1, 2 in the previous problem, but I didn't have to mention a direction because we've only got one variable. There's only one direction to go. We're only concerned with the positive x direction. So as a parallel problem, we need to state a point so that corresponds to the point 1, 2, but we don't need to state a direction. Because we're dealing with a single variable. What we have to do, so this will tell us how the function is changing when x equals 3. In the multivariable problem, I have to say, how is the function changing at the point 1, 2 in the direction of u or in the direction of v? So what we do is we look at the value of the function at that point, or we find the derivative. And then we plug in the point. So our linear approximation says at the point x equals 3, if x increases by 1, f of x increases by approximately 6. 1 is too big of a jump, because we know that if x goes from 3 to 4, we'll be going from 9 to 16, which is not a 6-point jump. But we can use this for linear approximations. If I have, so I know that this is, oh, so it's not gonna be too high. It's gonna be too high. That's not gonna be far enough either. Oh, I picked 3 and not 2. I probably need to finish the coffee before class. Oh, and it's also not on screen. So I'm just going to pretend that this is the point 3. So let's think about what we're going to use this 6 for. We can use the 6 to make a linear approximation of the function at the point 3. We don't have to worry about things like gradient because we don't have any directions that we have to worry about. There's only left and right. That's all we got. So we think we can make a linear approximation of f of x when x equals 3. So what do we need? We need the value of the function and so the linear approximation will be y equals 9 plus 6 times x minus 3. So if I move a little bit in the x direction, let's say to 3.1, I can approximate the function, and all I need is the 6. So if I use the linear approximation of the function when x is equal to 3.1, so let's approximate f of 3.1. I'll just use 9 plus 6 times 3.1 minus 3. So 9 plus 6 times 0.1. Here's our delta x. Here's the ratio of change in y to change in x. And here's where we start. So whatever this is, 9 point something. But the important piece is that this 0.1 is a delta x. The 6 is a delta y over delta x. And the 9 is where we start. We want to think in terms of these linear approximations when we're calculating these directional derivatives. If we're looking at a function of 2 variables and we're looking at gradients in the plane, then we have to have a whole surface. If we look at a particular contour, we calculate the gradient and we want to find, we can calculate how the function is changing in a whole bunch of directions, in any direction. Tangent to the plane will have 0 change. Perpendicular to the contour in the direction of the gradient will be maximum increase, and the negative gradient will be maximum decrease. What happened in this example, where we calculated the change of negative 46 over 5, is that we had the gradient going in the direction 2 and 13. So the gradient will be going in the direction of 2 and 13, and the direction 3, negative 4 would be, say, underneath on the other side of this tangent. Because we have maximum positive increase, drops down to 0 change, and then we'll go to maximum negative increase. So it must be that 3/5 minus 4/5 is down here below the tangent, because our dot product is negative. So since our function is decreasing in the direction of u, that gives us an idea about what direction u is relative to the gradient. This seems like a lot to think about, only because it's a lot to think about. And we have to think about this all the time in all of its details. So you want to start with being able to make the calculation. The first step is just learning how to make the calculation. Find the gradient with the partial derivatives. Calculate the gradient at a point. Make sure your vector is a unit vector, and then use the dot product to find the directional derivative. Remember what we know about the gradient. The gradient is the direction of maximum increase, and it will be perpendicular to the contour. Remember why this makes sense. Tangent to the contour, the function is not changing. Because tangent to the contour, we're just following along the contour, and the contour is where the value of the function is constant. We want to make sure that we and then try to compare what we've done before with single variable functions, where we calculate the derivative at a point and use that to tell us how much the function is changing approximately at that point, what direction the function is going at that point. We want to make sure that we understand this in it with these two-dimensional gradients when we're just looking at directions in a plane, because eventually we're going to apply this to function of 3 variables, and we're going to need to look at gradients in space. That's up next, gradients in space. I can't read anything in space without imagining it, without saying it, at least in my mind, as in space. This is all because of the Muppet Show. And one of the segments on the Muppet Show was pigs in space. And that's how they said it. And so now I can't say in space without saying it that way. This is why we should probably teach like younger children all of the mechanical bits of math, not try to explain anything to them except maybe arithmetic, and then just teach them all the algebra and like all these calculus maneuvers, because kids absorb that kind of stuff pretty fast. And then we just have to build the explanation around it. Any questions? Comments? Snide remarks? How's everybody, okay? All right. Certainly I've given you a lot to think about. It didn't seem like that. There's just like this one little calculation to make, but it's still a lot to think about. It's weird. Sometimes the simple ideas have complicated calculations, and sometimes there are complicated calculations for simple ideas. Like think about finding the derivative of a function using the definition of a derivative. Complicated calculation for kind of a simple idea. But then once we learn things like nx to the n minus 1, we have a simple calculation, and now the idea is more complicated. So I guess it's all relative. Thanks, Einstein. All right, that's going to do it for today. I will see y'all on tomorrow. Stick around if you have any questions. Everybody have a good day, and thanks for playing.